Just as it would be impossible to fly a large modern aircraft safely without the flight instruments, it would also be impossible to fly it safely without the engine and aircraft systems instruments. The engine instruments are divided basically into two categories that are called either the performance indicators or the engine condition indicators. Performance indicators are thrust indicating instruments, such as the engine pressure ratio (EPR) gauge or the fan speed (N1) gauge. Engine condition indicators include the exhaust gas temperature (EGT) gauge, compressor speed, oil pressure and oil temperature gauges. We'll be discussing these and others later in the lesson. This diagram shows some of the parameters that we've just mentioned, and the position of the sensors that are required to measure them. There are two types of cockpit display: the analog display, a clockwork cockpit, or the electronic display, a glass cockpit. We'll be showing some of the instruments required in the clockwork cockpit as we go through the lesson. The glass cockpit displays will be described in detail in the latter part of the lesson. In the clockwork cockpit, there is a multitude of gauges displaying information. The glass cockpit is displayed on cathode ray tubes, CRTs, or liquid crystal display panels, LCDs, with light-emitting diodes, LEDs, for digital displays. Alongside the glass cockpit display, a small number of conventional gauges are retained in case of failure of the electronic displays. Both types of display convey essentially the same information to the pilot, but the flexibility of the glass cockpit system means that it's now taking over as the preferred means of showing both flight and engine instrumentation. Thrust measuring instruments are of two basic types. The type that measures the jet pipe pressure, the P7 gauge. The type that measures the ratio of two parameters, the jet pipe pressure and the engine air intake pressure, the EPR gauge. Turbopropeller aircraft measure and indicate engine torque, which is used to give an indication of engine power. Older low-ratio bypass engines, like the Rolls-Royce Conway, use the jet pipe pressure, P7, as an indication of engine power. The P7 system gauge can be marked in inches of mercury, pounds per square inch, or a percentage of the engine's maximum thrust. High-ratio bypass engines use the engine pressure ratio, EPR, as an indication of engine power output. The ratio is that between the exhaust pressure and the engine intake pressure. On some large turbofan engines, the values of the turbine discharge pressure and the fan outlet pressure are integrated. The figure thus obtained is then compared to the compressor inlet pressure to produce what is called integrated EPR. Pitot tubes, suitably positioned, sense the pressures which are required to work the system. The tubes can either be connected directly to the indicator in the cockpit or to a pressure transmitter which is electrically connected to the indicator. Turboprops and turboshaft engines develop their power by producing a preponderance of torque to turn the propeller, rather than pure thrust from their jet efflux. Torque, by definition, is a force applied at a distance to a turning point. The torque meter system measures, and its indicator displays, the power being produced by the engine. There are two main methods employed in measuring the torque of the engine. One uses oil pressure, and the second is an electronic device. The units of measurement vary between systems. The indicator gauges may be calibrated to read pounds per square inch or foot-pounds, Newton meters, brake or shaft horsepower. Engine torque is proportional to the horsepower being produced by the engine, and this is transmitted through the propeller reduction gear. The helical gear torque meter system depends on the axial thrust which is developed when helically cut gears are used to transmit power through the propeller reduction gear. The shafts of the gears rotate within cylinders, and the axial thrust they develop is balanced by oil pressure trapped inside the cylinders. Torque meter oil pressure is transmitted to a gauge in the cockpit. The gauge is calibrated in pounds per square inch. The system oil pressure, which in some systems can have quite a high value, for instance the Proteus engine is capable of developing about 800 pounds of torque, is generated by a torque meter system oil pump. In this system, which is similar to that used on the Rolls-Royce Dart engine, there is an oil pressure bleed hole within each cylinder. When the thrust developed by the helically cut gear is exactly balanced by torque meter oil pressure, the shaft of each helical gear takes up a sensitive position, partially covering the bleed hole. If engine power output increases, the axial thrust being transmitted by each gear increases, which forces its shaft further into its retaining cylinder. Thus the shaft is forced into a new position where it blocks the bleed hole. The torque meter oil pressure, being unable to escape, now builds up to a new, higher value, until it's able to force the gear shaft back into the sensitive position, where once again it's able to balance the axial thrust being developed by the helical gear. If the engine power output decreases, the axial thrust being transmitted by each gear also decreases, which allows its shaft to be displaced slightly out of the retaining cylinder. Thus the shaft is forced into a new position where it uncovers the bleed hole. The torque meter oil pressure now falls to a new lower value, until the lower axial thrust being developed by the engine is able to overcome it and force the gear shaft back into the sensitive position in the cylinder. Once this has happened, axial thrust is again balanced by oil pressure in the cylinder, but now it's balanced by a lower torque meter value. In addition to giving an indication of engine power output, the torque meter system can also be utilized to send signals to the auto feather and the water methanol injection systems. The auto feather system, as its name implies, will automatically feather the propeller of a failed engine. This is particularly important if the failure occurs on takeoff. The electronic system comprises two concentric shafts. The first shaft, which is called the torque shaft, connects the engine to the propeller reduction gearbox. The second shaft, the reference shaft, is connected only to the engine. An exciter wheel is fitted to the forward end of each shaft. The exciter wheels rotate past an electromagnetic pickup and produce an AC voltage. While the engine is stationary, the exciter wheels are aligned, but as power is increased, the torque shaft twists. This changes the phase relationship of the voltages produced. The change in phase relationship, which is used to drive an indicator through an amplifier, is proportional to the change in power. The RPM indicator is called a tachometer, tacho for short. There are three methods of measuring engine rotational speeds: the mechanical magnetic tachometer, the electrical generator system, the tacho generator, the inductive probe system. The measurement of engine speed is of vital importance if accurate control and monitoring of the engine can be achieved. The crankshaft speed of piston engines is measured. The RPM indicator is called a tachometer, a tacho. The usual method of measuring engine rotational speed on piston engines is the mechanical or magnetic tachometer. The mechanical tachometer consists of a flexible drive shaft and the tacho indicator. One end of the flexible drive shaft is connected to the tacho indicator in the cockpit. The other end goes to the accessory drive casing on the engine, where it's driven through gears from the crankshaft. The input drive causes a magnet in the indicator to rotate. The magnet rotates inside a copper or aluminium drag cup. This induces eddy currents in the aluminium drag cup. Eddy currents are caused by the magnetic field of the moving magnet acting on the electrons of any metal in the vicinity of the magnet. The eddy currents themselves generate a magnetic field which interacts with the magnetic field of the magnet. This interaction causes a torque or turning moment, which is established to turn the drag cup in the same direction as the permanent magnet. A shaft extends from the drag cup and is connected to a pointer. The turning motion of the pointer is against the tension of a hairspring, which controls the drag cup position and hence the position of the pointer. The flexible drive is driven at reduced speed, but true speed will be shown on the indicator. The indicator incorporates compensation devices for changes in temperature. The electrical generator system, sometimes called the tachogenerator system, is possibly the oldest form of engine speed measurement still in use on large aircraft. It utilizes a small three-phase generator, driven by the appropriate spool shaft. The output of this generator powers an indicator in the cockpit. The indicator is a synchronous squirrel cage motor that turns a drag cup assembly. The drag cup moves a pointer over a scale in a similar manner to that which we've just seen used in the mechanical system. In older aircraft, the indicator showed the actual revolutions per minute of the engine, but it's much more common to have the speed displayed as a percentage of the maximum engine speed. The speed of rotation of each of the spools is displayed. N is the SI symbol for rotational speed. Thus, in a triple spool engine, the speed of the low-pressure compressor, the fan, would be displayed as N1. The intermediate spool speed would be shown as N2, and the high-pressure compressor rotational speed would be N3. It's probable that there would always be provision on the high-pressure compressor spool for driving a tachogenerator through the external gearbox, which is driven by the high-pressure compressor shaft. But it may not always be possible to have gearboxes driven by the other compressor shafts. In this case, a speed probe could be used. There are two ways that the speed probe can generate the pulses required to feed the system. The first method uses the fan blades to excite the magnetic field of the sensor head of the speed probe as they pass it. The excitations generate a waveform which has a frequency proportional to the rotational speed of the fan. The second system uses a phonic wheel, which is part of the compressor shaft. The teeth of the phonic wheel pass through the magnetic field of the sensor, and thus generate pulses at a frequency which is proportional to the rotational speed of the shaft. The output of the sensor is amplified before being sent to the gauge. The advantage of the speed probe system is twofold. First, the reduction in the number of moving parts required in the engine, and second, that a number of separate electrical outputs additional to those required for speed indications can be provided, for example, automatic power control and flight data acquisition systems. RPM indicators which receive their speed signals directly from speed sensors, or via servo-operated systems, are powered from the aircraft supply. In the event of either a power supply failure or a signal failure, the needle of the indicator is returned to an off-scale position, and a power-off flag may be displayed. Clockwork cockpit instruments have displays which show percentage rotational speed, with 100% corresponding to the maximum spool RPM. Two scales are used: a main scale calibrated 0 to 100% in 10% increments, and a second pointer displays rotational speed in 1% increments.